Alrighty, so now we know that charged objects can exert forces on each other. We've seen that. And you've seen the electroscope simulation to see how those charges move around within an object. Okay, what about quantifying charge? We do have devices called charge sensors that you could use to quantify a charge, right? So we could say there's an object that has a charge of negative 75 nanocoulombs. All right. What does that mean? Well, negative 75 nano means times 10 to the minus 9 coulombs. All right. So it seems like a pretty small charge, even though what we'll find here in just a little bit is that a coulomb is a whole heck of a lot of charge. What does this negative mean? Well, it means there are more electrons in a material than there are protons. Okay, so we'll call that a negative means extra electrons. Okay, and sometimes instead of writing out electrons as a word, sometimes I'll use a common abbreviation for electron, which is an E with a little minus sign. Okay, so again, negative charge means extra electrons. Positive charge means there are more positives than there are negatives, so we can call that missing electrons. All right, so what charge does one electron have? Okay. Well, one electron has what's called an elementary charge. And that doesn't mean it's in like second grade or something. Elementary charge is actually the smallest amount of charge something can have. It's the charge of one electron or one proton. Charge for one electron or proton. So an electron has this charge, but it's negative. A proton has the same charge, but it's positive. All right, and that elementary charge, we abbreviate it. Sometimes it's Q with a little e subscript. Sometimes it's just a letter E, and it has a value of 1.6 times 10 to the minus 19 coulombs, and that's the number of coulombs per electron, right? Whether it's missing or extra. All right, so if we know an object's charge, right, if we know that something has a charge of negative 75 times 10 to the minus 9 coulombs, and we know one electron is 1.6 times 10 to the minus 19 coulombs, could we figure out how many extra electrons there are? Man, my handwriting is horrible today. Sorry, you guys. How many extra electrons? Well, if we know the charge and we divide it by how much charge there is per electron, we can get the number of extra or missing electrons. Okay. And we abbreviate the number of extra or missing electrons with a capital N, literally N for number. So the number is the charge divided by how much charge there is for a single one. Okay, Now, I'm going to put absolute value signs around this charge because otherwise we'll kind of get ourselves confused. All right, so whether the net charge is negative or positive will tell us whether they're extra or missing electrons. But we don't want to get like a negative charge to give us a negative answer for a number, because if we had like a negative number of electrons, we would assume that means you're losing electrons. Does that make sense? So we want an absolute value sign around this charge, and so we'd say negative 75 times 10 to the minus 9 coulombs divided by 1.6 times 10 to the minus 19 coulombs per electron. And that will give us 4.6 times 10 to the 11 extra electrons. Okay. So that's how we do that. If we knew the number of extra electrons, we could multiply by the elementary charge to get the charge associated with that pile of extra electrons as well. We could go in that direction. Okay, so that's one of the skills that you need to know how to do. Given a charge or a number of electrons, can you figure out the missing piece? Okay, next up, we've got the law of conservation of charge. Okay, so what we were noticing when we were doing the electroscope simulation is that during any of the processes, the net electric charge in an isolated system is remaining constant. Okay, so what that really means is there aren't going to be any electrons that hop off a material and ionize an air particle, right, for our purposes, right? If we're starting out with a certain number of electrons and protons, that's what we're going to have when we are all done. Okay, no electrons will be lost in the making of these problems, okay? All right, so for example, let's say we have two objects. Okay, one object has a charge of positive 2 coulombs. Another object has a charge of 0, right? It's neutral. So when they come together and they touch, okay, they together will have a net charge that is positive 2 coulombs. Does that make sense? Okay, you just combine the two charges to come up with a net charge. Two objects, when they're touching, they'll want to equalize their charge. And then when those two objects separate again, that means each separated object will split the charge that they had together. So that means this will have a positive 1 coulomb charge, and this one would have a positive 1 coulomb charge, right? Before they touch, they have a net charge of positive 2 coulombs. After they touch, they together have a charge of positive 2 coulombs. And then when they separate again, right, they together have a charge of positive 2 coulombs, right? The total charge has been conserved in that interaction. Okay, we can try it again. What if we have -3 and positive 2, right? They come together and they touch. Okay, just kidding. They're going to touch, right? And together they will have a charge of -1 coulombs. And then they'll separate. And that means each object will have a charge of -0.5 a coulomb. Okay, so I intentionally left units on here. So we've got negative half a coulomb, which is still a ginormous amount of charge. Instead of saying 1/2, I don't want you to get the idea that you can take an electron and split it in half. You can't have anything that has half the charge of an electron. Okay, any charge that an object has will be will have a factor of 1.6 times 10 to the minus 19 coulombs. Okay, so we're not splitting electrons here. Okay, but we're splitting the total charge. All right, so here's an example. An object is metallic and electrically neutral. So metallic just means that charges can move around easily. We've got an electric conductor. It's electrically neutral, which means we're starting out with an equal number of positive and negative charges. Okay, it's charged by induction, and so that it acquires a net charge now of negative 3 times 10 to the minus 6 coulombs. All right. So this charge by induction business doesn't matter. What this problem is saying is that we had a metallic object that was neutral, and then we put some negative charge on it, and now this is its charge, right? This is its charge. Were electrons transferred onto or off of the sphere? Okay, so it was given a negative charge. That means electrons were transferred onto. Electrons transferred on. Okay, how many electrons were transferred onto the sphere? Well, we know that we've got a charge that's equal to negative 3 times 10 to the minus 6 coulombs. We know the elementary charge is 1.6 times 10 to the minus 19 coulombs per electron. And then we're looking for how many extra electrons that is. Okay, so we can simply use N equals the absolute value of Q over E, negative 3 times 10 to the minus 6 over 1.6 times 10 to the minus 19. And we end up with 1.88 times 10 to the 13 extra electrons. Boop. Cool. A whole ton of extra electrons, right? Times 10 to the minus 6, that's like a millionth of a 3/millionths of a coulomb of charge, right? That's still like a number I can't even say. Times 10 to the 13. A whole bunch of electrons for such a tiny, tiny little charge. Okay. All right, now we want to take a look and say object B is identical to object A. It's a conductor. Charges can easily be transferred in between the two. Object B is electrically neutral. The two objects touch. Okay. So what this is telling us is if we do just like we did on the previous slide where we've got two objects, object A has a charge of negative 3 times 10 to the minus 6 coulombs, and object B is neutral. It has a charge of 0. When they come together, right, they will together have a charge of negative 3 times 10 to the negative 6 coulombs. Okay, and then they'll separate and they will each split. So negative 1.5.